All right, hi everybody, it's Professor Mitchell. We're going to wrap up our work with chapter 4. You may remember I mentioned at the beginning of the chapter, we're not going to do section 4.5. So this is the last section in chapter 4 that we're going to do, section 4.4 on counting. So let's count some stuff. All right, this section requires much greater use of formulas as we consider 5 different methods for counting the number of possible outcomes in a variety of situations. And I'm going to revise that a little bit. We are not necessarily going to have to use the formulas a whole lot because many of them are built into the calculator. All right, so if you want to use the formula that's built into the calculator, that's just fine. Okay. All right, so we're going to start with what they call the multiplication counting rule. And the tired old cliche example of the multiplication counting rule is this. Suppose that I have just done my laundry and I reach into my clean laundry basket and there are 4 shirts and 3 pairs of pants. How many different outfits can you put together if you have 4 shirts and 3 pairs of pants? So an outfit is determined by your shirt and your pants. If you change either one of those things, it's a different outfit. Okay? So think about, do you know how to use the 4 and the 3 to get that answer? Okay. And the answer is 12. You can make 12 different outfits. The idea is, let's say that these are your 4 shirts. Shirt 1, shirt 2, shirt 3, shirt 4. With any one of those 4 shirts, I can put a pair of pants. Let's say that either all my stuff matches or I don't care. All right. Okay. So since you can put any one of 3 pairs of pants with any shirt, that makes it 4 times 3. Okay? So I do the same thing here, I do the same thing here, and I do the same thing here. So each one of these at the end represents a different outfit. Okay? That is the tired old cliche application for the multiplication counting rule. Okay? So the way that it works in general is for a sequence of events in which the first event can occur n1 ways, so n1 is some number. The second event can occur n2 ways. So in this tired cliche example, the first event is pick a shirt. The second event is pick a pair of pants. And you could extend this to any number of things. I could include socks, I could include shoes, whatever I want. Okay, but the point is that you multiply all those numbers together. Okay? So if your first selection can be made n1 ways, your second selection can be made n2 ways, et cetera, et cetera, et cetera. The total number of outcomes, you just multiply all those numbers together. Okay, so here's an example of the multiplication counting rule. When making random guesses for an unknown 4-digit passcode, think like your ATM PIN number. Each digit can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. What is the total number of different possible passcodes? That's the first question. And then the second question is, given that all of the guesses have the same chance of being correct, what is the probability of guessing the correct passcode on the first attempt? Okay. All right, so the first question is, what is the total number of different possible passcodes? So first thing you have to think about is how many choices do you have for the first digit? It can be any number 0 through 9. That would be 10, right? You have 10 choices for the first digit, 10 choices for the second digit, 10 choices for the third digit, 10 choices for the fourth digit. So we're picking digits with replacement. Okay. There's no rule that says in your ATM PIN number you have to use all different numbers. Okay. So the total number of different possible passcodes is 10 times 10 times 10 times 10, which is 10,000. And that kind of makes sense. If you think of these passcodes as numbers, you've got the numbers 1 through 9,999, but then you also have 0, 0, 0, 0. So that's the 10,000th one. And because all of the passcodes are equally likely, the probability of getting the correct passcode on the first attempt is only 1 in 10,000, 0.0001. Okay, so if you drop your ATM card, you don't have to worry too much about somebody picking it up and guessing your PIN number on the first try. Just don't write it on the card or anything like that. Okay. The next counting rule is called the factorial rule. This is a special case of the multiplication counting rule. All right, so my tired old cliche example for this is you have 4 books to arrange on a bookshelf. And the question is, how many different ways are there to arrange the books? I don't have 4 books within reach right now, so I'm going to pretend that these are books. Okay. So I go to pick the first book to put on the shelf. Let's say I'm putting them from left to right. So when I go to pick that first book, I have 4 choices. So let's say I pick this one. Okay. Put that on the shelf. I go to pick the second book, I have 3 choices, right? So I pick the second book, and let's say I pick this one, I put that on the shelf. Third book, I have 2 choices, so I pick one of these. And by the time I get to the last book, there's only 1 choice. So using the multiplication counting rule, there are 4 times 3 times 2 times 1 ways to put the book on the shelf. So we're starting with the number 4 and multiplying by every smaller number until we get to 1. And that comes up in so many different counting problems that somebody came up with a special notation for it. So I like to joke that I wish that this notation was read n, all right? But it's not, it's read n factorial. And what it means is start with the number n and multiply by every smaller number until you get to 1. Okay. So for example, 4 factorial is 4 times 3 times 2 times 1, which is 24. Okay. The number of different arrangements, order matters, of n different items when all n of them are selected is n factorial. Okay. So these are selections without replacement. Okay, so like arranging books on a shelf, once you pick one book to put on a shelf, obviously that same book can't appear again later on the shelf. Okay. Factorial symbol denotes the product of decreasing positive whole numbers. Now there is such a thing as 0 factorial. By special definition, 0 factorial is equal to 1. Okay. And really the main reason for that is that we use factorial in a lot of different formulas. And in order for those formulas to work the way they're supposed to work, we kind of have to define it that way. Okay. Otherwise you wouldn't be able to use this explanation that I showed you here. You know, start with that number and multiply by every smaller number till you get to 1, because 0 is already less than 1. Okay. All right, so the factorial rule is based on the principle that the first item can be selected n different ways, second can be selected n minus 1 ways, et cetera, et cetera. Okay, so again, it's just a special case of the multiplication rule. Okay, official example for factorial rule. A statistics researcher must personally visit the presidents of the Gallup, Nielsen, Harris, Pew, and Zogby polling companies. These are all real polling companies. So the first question is, how many different travel itineraries are possible? Okay, meaning he's going to visit Harris first, Nielsen second, Pew third, et cetera, et cetera. So how many different ways are there to do that? And then the second question, if the itinerary is randomly selected, what's the probability that the presidents are visited in order from youngest to oldest? Okay. And so you know what, if you're watching the video, I'm going to ask you to pause and think about that for as long as you need to. And then we will come back and compare notes. Okay. For those 5 different presidents, the number of different travel itineraries is 5 factorial. 5 times 4 times 3 times 2 times 1 is 120. Okay. So before we go any further, I just want to show you how you can use your calculator to do that really quickly. All right, 5 factorial, I don't really mind going 5 times 4 times 3 times 2 times 1. If it was 11 factorial, maybe I'm going to get a little bored doing that. So I really only have one kind of calculator that I can actually press buttons on, and that's this one right here. I do have a picture of a scientific calculator, so I can at least show you which button to press first. All right. So the way this works on a graphing calculator is you press the number that you want to factorial, like 5, and then you press math, and it brings up this menu. All of this stuff for counting is under PRB for probability. Okay. And then for factorial, we're going to go down to number 4. Okay. So you press enter. There's 5 factorial. I press enter again, and it tells me it's 120. Okay. The way it works on a scientific calculator, I can't show you the whole thing, unfortunately, but here's what your scientific calculator looks like. That PRB function that we just looked at on the graphing calculator, that's got its own button right here. Okay. This is the calculator that I use. So you press that PRB button, and then I think what it does is it just gives you 3 options along the top, and factorial is one of them. Okay, so you press PRB, or hit the number that you want to factorial, like 5, and then press PRB, and then just scroll over to wherever the factorial is. Let me just look here real quick. Let me see, can you see this? I think you can see that. All right. So the factorial is over there on the right. Okay. So I arrow over to the factorial. I press enter. There's 5 factorial. I press enter again, and I get my 120. Okay. So that's how you can use the calculator to get your 120. Okay. There was a second question. The second question said something like, if you pick a random itinerary, what's the probability that it's the one that has you visiting the presidents in order from youngest to oldest or something? So that's kind of similar to the first probability question they asked about guessing the PIN number. There's only going to be one itinerary that is in that specific order, visiting the presidents from youngest to oldest. So the probability of picking that itinerary would be 1 over 120. Okay. All right. The next thing, is permutations. Permutations of items are arrangements in which different sequences of the same items are counted separately. All right, and I have a couple of unofficial examples that I think will help you understand the difference between that and the other thing we're going to talk about. So for example, the letter arrangements ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as 6 different permutations. So with a permutation, I care about order. Order matters. Different thing, or the same things in a different order are counted as different things. They're not the same thing. Okay. On the other hand, Combinations are what I use when I don't care about orders. So think, let's say I have 5 people in my club and I need 3 of them to be on a committee. If the people on the committee are all serving the same role, you know, I'm not going to have a committee chairperson or anything like that, then all these things here would be counted as the same thing. Okay? It's the same 3 people on the committee. I don't care what order they're in. Okay? All right, so they have this cute little mnemonic device to help you remember the difference between a permutation and a combination. I have never seen this before. Remember permutations position and combinations committee. So permutations position means the position is important. So this would be like if you were picking your 3 people to be the president, the vice president, and the treasurer of the club. All right. And that's actually, I built in an unofficial example that uses that. But if you're just picking the 3 people to be on the committee and you don't have any specific roles for the 3 people, then I don't care what order they're picked in. Okay. And this next thing is something that I don't remember where I saw this. Maybe somebody put it on my Facebook. I don't remember. If the order on a combination lock is important, and it is, then why isn't it called a permutation lock? Right. So that is not a good way to remember the difference between a permutation and a combination. Do not think about combination locks, all right? Because with those, order is important. Okay. All right, so permutations rule. So here is my unofficial example. Suppose you need to pick 3 people out of Alice, Bob, Carol, Doug, and Evelyn. These were the first 5 names I thought of that started with A, B, C, D, E. To be the president, the vice president, and the treasurer. In how many ways can this selection be made? Okay. Well, this is really just a multiplication rule problem, multiplication counting rule, that first rule we talked about. So when you go to pick the president, you have 5 choices. When you go to pick the vice president, you only have 4 choices because you're not going to let the same person be both. And then you need a 3rd different person to be the treasurer. So you have 3 choices for that, right? Okay, now, don't worry about all this extra stuff I showed over here. Really, if you were doing this problem, all you would have to do is 5 times 4 times 3 equals 60, okay? The reason for this other stuff is that I am about to show you a formula to solve this problem. And so I'm trying to make this look more like the formula, okay? So this 5 times 4 times 3 is sort of like a factorial, except you're not going all the way down to 1, right? So to make this into a formula that I can write using factorials, I am going to go all the way down to 1, but then I'm going to make up for it by dividing out the numbers that I don't need. So again, you would not solve the problem like this. I'm just showing you where the formula comes from. So 5 times 4 times 3, that can be written 5 times 4 times 3 times 2 times 1, divided by 2 times 1. The top of that is 5 factorial. The bottom of that is 2 factorial. And now I'm going to go one extra step to show you the numbers that were in the problem, which is that I had 5 people and I needed to pick 3 of them. That's how you can make this formula where you would put the numbers 5 and 3. Okay. All right, so here is the formula for that. When n different items are available and r of them are selected without replacement, so this is another without replacement situation, the number of different permutations, okay, so this again means I care about order, is given by this formula, okay? This formula is also built into the calculator. So if you never ever use this formula by hand, that's just fine with me. Okay, so I'll show you how to use the formula to do this next example. Okay, so here's the official example. In a horse race, a trifecta bet is won by correctly selecting the horses that finish first, second, and third in the correct order. Okay, so that's a very difficult bet to win. The 140th running of the Kentucky Derby had a field of 19 horses. So what they're getting ready to ask me, spoiler alert, is how many different ways could I select my trifecta bet? Okay. And then what's the probability of picking the one that matches the, specific 3 horses? I want to be very careful how I say this, and I'll tell you why in a minute. Okay, so question number 1, how many different trifecta bets are possible? Again, 19 horses, you have to pick 3 in the correct order. If a bettor, and then part B, if a bettor randomly selects 3 of those horses for a trifecta bet, what's the probability of selecting California Chrome to win, Commanding Curve to finish second, and Danza to finish third? All right, so what's the probability that you would randomly pick those 3 horses? And they are the horses apparently that ended up winning, all right, or coming in first, second, and third. And then here's an interesting question. Do all of the different possible trifecta bets have the same chance of winning? All right, it is possible for horses to tie, and we won't think about that. Okay. So those are the questions. So let's start with how many different trifecta bets are possible. So I have 19 horses. I need to pick 3 of them, and I need to pick them in the correct order. Okay. So that is a permutation problem. So I put 19 for N, I put 3 for R. So this ends up being 19 factorial divided by 16 factorial. That comes out to 5,814. All right, to do that problem on the graphing calculator, you would do this. You would press 19 and then go into that same math menu. You hit math and then go over to PRB for probability. And then NPR is number 2. See it there? So you press enter on that. Let me press enter on that and then put the number 3. Okay, so we have 19 horses. We're trying to pick 3 in order. Okay. You press enter on that and you get the same 5,814 that they got. Okay. So that's if you're using the graphing calculator. If you're using the scientific calculator, here is the scientific calculator again. So you press 19 and then you go into this same PRB. You press that PRB button again, which is right here. Okay, so I'm going to try to do this for you watching the video. All right, I'm starting by pressing 19. And then I'm going, you know what, it'd be easier if I do it from behind the camera. Okay. Press PRB. And then it's the very first one right there. Press enter on that. And then press the number 3. And there's your 5,814. Okay. Okay. So since there are 5,814 different possible arrangements, randomly selecting the one that has a particular 3 horses coming in first, second, and third, the probability of that happening is 1 out of 5,814. Okay. However, remember they also had this question about are all of these permutations equally likely to hit the trifecta? And the answer is that they are not, because some horses are faster than others. Some horses are favored to win over others. Okay, so these trifectas do not all have the same chance of winning. Okay, if you think back to when we talked about actual odds against and payoff odds, a $2 bet on this race, a winning $2 bet in this race, only won a little bit more than $3,400. If these 5,800 outcomes were equally likely, then that $2 bet, if the racetrack was not trying to make any money, you know, using actual odds as the payoff odds, that $2 bet should have paid over $11,000. Okay. Now, of course, they don't pay based on actual odds, but still, usually it's not cut down by that much. All right. If the actual odds against this trifecta winning match this probability, then I would still expect that payoff to be a lot more than $3,400. Okay, it's because this trifecta was probably one of the more favored ones to win. Okay, they are not all equally likely. Okay. All right, this is an interesting one. I was a little surprised that they got into this. Permutations rule when some items are identical to others. All right, so I was trying to think of an unofficial example to do kind of on the fly, and this the last time I did this, and this is the one I came up with. How many ways are there to arrange the letters in the word different? Okay. So what's special about the word different is that the letters are not all different. If they were all different, that would be a lot easier. It would just be 9 factorial, right? You have 9 choices for the first letter, 8 choices for the second, 7 for the third, et cetera, et cetera, et cetera, et cetera. Okay. So if the letters were all different, there would be 9 factorial ways, but they're not. There are 2 letter F's and 2 letter E's. Okay. So here's how we're going to fix it. For each arrangement of letters, there are 2 factorial times 2 factorial, which is 4, that are actually the same. And I've written them down here. So imagine that you attach little subscripts to the F's and the E's to make them look different. So here is my, let's say, my original arrangement of the letters. I could switch the F's, and that would give me one that looks the same. Or I could switch the E's, and that would give me another one that looks the same. Or I could switch both. Okay. So there are 2 factorial ways to arrange the F's. There are 2 factorial ways to arrange the E's. Okay. So again, for each arrangement of letters, there are 4 that are actually the same. So if you want the accurate count of how many ways are there to arrange these letters that actually look different, there would be 9 factorial divided by 4, which comes out to 90,720. Okay. So I'm about to give you a formula for this. You will never have to do this kind of problem exactly like this. You can just use the formula. I just wanted to give you an idea of where the formula came from. So here's the formula. The number of different permutations, again, order matters. When n items are available and all n of them are selected without replacement, but some of the items are identical to others. The way that you find that number of different arrangements is you start with n factorial, but then you divide by these numbers that represent how many of them are alike. All right, so n1 of these things are alike, and then another n2 are alike, et cetera, et cetera, et cetera. So in my problem that I just showed you, n is 9. There are 9 letters in the word different, but I'm going to divide by 2 factorial, which represents the F's, and then another 2 factorial, which represents the E's. And that's all I have to do because all the other letters are different. Okay. All right, so here comes the official example. When designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. All right. So for one particular survey with 10 questions, 2 of the questions are identical to each other, and then another 3 are also identical to each other. So another way that they catch people, you know, just filling out a survey and not really paying attention is they'll ask them a bunch of questions. You know, do you like this? Do you like that? Do you like this other thing? And they wait for people to say yes, yes, yes. And then they'll throw in a, and do you dislike this thing? And they want to see if people will answer no. All right. If people just answer yes to every single question, then they figure maybe this person wasn't paying attention. For this survey with 10 questions, but 2 of them are identical to each other, and then another 3 are also identical, how many different arrangements are possible? And then their follow-up question this time is it practical to survey enough subjects so that every different possible arrangement is used? Okay. So they're asking how many ways are there to put the questions in order? Okay. That's another surveying technique that is sometimes used is they'll jumble the order of the questions and see if that makes any difference. Hopefully it doesn't. You know, but sometimes people get tired of filling out the survey. They'll stop partway through, you know, so that's also a way of getting all the, each individual question to be answered enough times, okay? So you have 10 questions with 2 that are identical to each other and another 3 that are also identical. So the number of different ways to put those in order would be 10 factorial divided by 2 factorial times 3 factorial. Now this formula is not built into the calculator, and just a second here because I noticed there is a minor typo on here that I have not gotten around to fixing. This K here should be a subscript. It should be like this and not like this. So ignore the big K and put a little k there. Okay, that's a minor typo. So this formula is not built into the calculator. You have to use the factorial. So the only thing I'm going to caution you about with this formula is this. When you put that into the calculator, let's get rid of this. And let's get rid of this. Make sure that you put that 2 factorial times 3 factorial in parentheses. Otherwise, it's going to do some order of operations thing that you don't want it to do. Okay, so 10 factorial divided by, and now I'm going to put parentheses. And then I'm going to put my 2 factorial 3 factorial. And I don't think you have to put a times there. I think it understands that means times. Okay. So what answer did they get? 302,400? Yes, there it is. Okay. Yeah, if you don't put the parentheses, then what it's going to do is divide by 2 factorial and then multiply the whole thing by 3 factorial. And that's not what you want it to do. All right, so real quick, there was another part to this question. So let's deal with that. Looks like this video is going to have a part 2 that's going to be very, very short because we're almost finished with this section, but not quite. Let me get rid of this. Okay. So the question was, would it be possible, I forget what word they actually use, to survey enough subjects so that every different arrangement is used? The answer is probably not. Okay. It is not practical to accommodate every possible permutation. Surveys just don't go out to 300,000 people. All right. Usually about 1,000 is a typical sample size, like if you're running a survey. Okay. 300,000 would be too many. Okay.